Hello and welcome. Here we are in lecture 17. So we'll be continuing where we left off. And as part of this 3 lecture sequence talking about kind of these physical implementation concerns. So remember last time we talked more broadly about what's possible. And today we're going to talk in hard design, physical design, kind of what's going on there, what we can optimize. And today we're going to specifically zoom in on delay and what are kind of aspects related to delay, what can we do about delay, etc. And then next week, we'll be talking about a little bit about power and design space exploration. It's kind of the next stage of that kind of physical concerns. We'll also have a great guest lecture on Wednesday. We're going to learn about some of the formal verification capabilities available in Schedule 3.5. So that should be really exciting. Okay, so let's talk about delay for today. Particularly, we're going to talk briefly about, just to give a bit of physical intuition as to, why is there delay? So as a reminder, we aren't trusting folks to have a huge EE background to take this course. So we're going to give you kind of a little bit of a primer on what's going on there and why there is some sources of delay. We'll talk about what we can do about it. So there will be code at the very end of this. I'm going to go ahead and load a notebook. Hopefully that goes through. Yep. Okay. So let's talk about delay, right? So where does delay fit into the whole picture? Remember we were talking about PPA last time? Power, performance, area, right? So it's not power area, but it's performance, right? Which just, corresponds to how long something takes to do. Now, of course, there's the delay it takes in a circuit, and there's also some notion about what's your clock frequency in your clock period, how much parallelism you have. For now, we're talking about just the delay, because realize that's going to, of course, impact us in many ways, right? So how long does it take a certain circuit to do something? Well, that's a delay. And there's multiple sources of delay, right? To kind of zoom out and broadly characterize them, we could say there's delay associated with the gates and delay associated with the wires, right? And the wires can be non-trivial, right? The wire is going to go a certain distance or whatnot, right? And so I think some of these perhaps, it's intuitive that there should be physical costs to these things, right? In order for a collection of transistors we call a logic gate to perform an operation, it takes some time for them to, charge and discharge and perform the effective switching operation, right? And of course, for a wire, it takes a certain amount of time to charge or discharge that wire. Now, these delays are not static, right? So you can imagine, depending on the complexity of the gate, and perhaps even its current state in terms of ones and zeros, to change another combination of ones and zeros, that may take a certain amount of time. When it comes to wire delay, not only is there, there's effective capacitance and resistance of the wire, which is determined by not only how long the wire is, but how many things is it attached to, etc. And then for the actual gates, right, some things to be concerned about is this fan out, this notion of I have, one output being read in multiple places, that's fan out. And so how many times it fans out, that's going to slow it down more, right? The more you broadcast a signal, the more, load is placed on this wire, and the longer it takes to charge or discharge this wire. And so as a designer, right, we kind of want to optimize both of these, right? And so, depending on, how you optimize your circuit, you perhaps could choose, fewer gates or faster gates. That would be great. When it comes to wire delay, usually we use automated tools for placement and routing. So for placements, we put the components down on the device, and then routing is connected in with wires. There's still some things we can do as a designer to impact that, right? We can perhaps try to reduce the fan out, right? If we, don't need to fan out 1,000 ways, instead only needs to fan out 2 ways, that's going to make a huge difference in the delay. Additionally, we kind of go through all this, right? There's some contrast that's worth pointing out between ASICs and FPGAs, right? Where in an ASIC, for example, an actual custom chip, if you have, a nice optimized design that doesn't have a lot of fan out and it's well placed, your wire delay is substantial, but not, that big in the grand scheme of things, right? Assuming it's all local kind of signaling you're doing. Now, if you're on FPGA, even if you're trying to go local, the routing delay, the wiring delay is much, much more pronounced, right? So sometimes, the majority of a delay in the critical path in an FPGA actually is probably due to wire delay, right? So their placement really matters. Understand FPGA, of course, because it's able to reconfigure itself. There's some amount of, extra capacitance and loads kind of charge and discharge, and longer routes it needs to go to kind of avoid things or to reach other resources. So wiring delay is perhaps more of a concern for FPGAs, but both delays matter in both target technologies. Okay, and then what are the units for delay? Well, normally you might say, oh, let's talk about in terms of some time, right? So we should use time units, right? And because it's so fast, we're talking picoseconds, right? Nanoseconds is more for, delays, maybe a few decades ago, but, now if you're running in the gigahertz range, right, gigahertz clock frequency, that means your clock period is a nanosecond or less. So thus, it's probably best to talk about delays in terms of tens or hundreds of picoseconds, right? In terms of how long a certain gate takes. But that's very, sensitive to when we're talking about this, right? Right now we're talking picoseconds. 20 years ago, they were talking picoseconds, but maybe they also were still talking about nanoseconds some of the time. And you can kind of see over time as we go faster and faster, the time unit changes, right? And, saying this gate takes a certain amount of time in one technology and then use a very different technology, that's going to kind of change the trade-offs for that, right? So one way of dealing with this is this kind of normalized metric called FO4, or fan out of 4. So if you ever go to a conference or read some papers, you might see this come up. And so what they do is they say, if we have an inverter driving 4 inverters like we have down here, this is kind of a good proxy for kind of how fast this technology is, right? You can imagine for a given technology, some gates are faster or slower, and then another technology, maybe which gates are faster and slower kind of changes a little bit. But the first order, most important thing is which technology you're using. And FO4 is kind of a way to normalize to a given technology, right? So for a given technology, you'll see, one inverter driving 4 inverters is kind of a good proxy for what's a reasonable gate and a reasonable load on it. How long does that take, right? How long does it take this inverter to flip the input to all of these other inverters? And that unit is then divided by the time, right? So let's say this takes, some amount of time, right? In this case, they found for Intel Pentium 4 20 years ago, that was 18 picoseconds, right? So if someone else has a critical path that, is, let's say, 180 picoseconds, so we divide it out and say, oh, wait, that's a 10 FO4 critical path. So this unit's really helpful because you talk about designs across technologies, right? So amongst computer architects, you can say, oh, I'm looking at, an out-of-order processor design, and I'm really trying to push it. I'm trying to go sub 20 FO4, right? And that's a really aggressive out-of-order design of a very deep pipeline, so to speak, right? As opposed to maybe you're saying, I'm fine going in the 30s in FO4, right? That's okay. And so this is kind of a nice normalized metric where you can kind of talk about things that's not quite so technology dependent. Now, it's not perfect, right? It's, a lot of caveats, things like operating voltage, and, if a given technology, how the inverters compare to the other gates will change, but it's still there's some chance to compare across technologies, right? And this is one of the things that happens in computing we sometimes forget is, because of Moore's law, where we get so many transistors, we've had this exponential changes over the years, right? And so in some ways, a lot of things across that time period often aren't comparable. And so it's kind of amazing that with something like FO4, we kind of actually can compare some things, right? Okay, I'll pause for any questions so far. Okay, well, let's keep going. So we've talked about, what caused delay, how would you measure it, why do we care so much about it? Well, the reason why I care so much about it is something called the critical path, right? And this is what's going to set our clock frequency, right? So if we're able to have a faster clock frequency, unless we have hazards, our design is going to produce results faster. So this is kind of, the heartbeat of the system, right? And if you have a heart beating faster, you can get more done, right? Your heartbeat when you're sitting is very different than heartbeat when you're running full speed, right? And so if you're able to maintain that high heartbeat, right, then things work out, or you get things done faster, right? And so in terms of the clock period, how it fits in, right, is, within a clock period, you need to get the results out of a register, through whatever logic you have, and into the input of the next register before the next clock period, right? If that takes too long, the register is going to see the wrong value, and you're going to have a corrupted design, right? And so it's important that the critical path delay be less than the clock period delay, right? So that way that the longest path has time to settle. That is, the end of this logic path, which is being fed to register somewhere, has time to be a perfectly stable signal before the register reaches value and, moves on to the next cycle. So, we pick our clock frequency, we're basically picking it based on this critical path delay, right? And, so the thing about the critical path is that if there's some other path, perhaps like going through up here, which has, less logic delay, and that's shorter or faster, that's not going to affect the clock frequency, right? We don't care about that. All we care about is this critical path, the one that's really kind of holding us up, right? And so this critical path actually comes back to get us two different ways, right? Because it's going to set what the clock frequency is, right? So like I said, you can go no faster than a critical path. So if you have a shorter critical path, you can go faster. But going faster isn't the only way you can use that benefit, right? Let's say your clock frequency is already at the performance level you need. Why would you reduce your critical path? Well, if you do that, you actually can shorten the critical path to be significantly less than that frequency, which so far at first wouldn't seem like a benefit. But then you have the opportunity to save energy by turning down the supply voltage. So if you run your circuit at a lower voltage, it's going to go slower, but also take less power, right? And so this is kind of a really interesting thing, right? If you kind of have some amount of hardware and it's, solving a problem at a certain rate, right? And if you're able to kind of change the critical path, that same hardware is going to be able to solve the same problem at the same rate for less energy, right? That's pretty cool. And so, yeah, so if you can reduce your critical path, even if you don't actually run any faster, you can actually just run at a lower voltage, kind of to slow down to match your requirement, right? And you can do this, right? And so some people refer to this kind of, crawling to meet a deadline. That's kind of the way to think of this, right? It's not a very snazzy title, but that's the way you can really save energy. So even though in a modern era where we're mostly power limited or energy limited when we're designing, reducing the critical path is extremely important because, it's going to help set your frequency. It's also going to be an opportunity for you to perhaps run slower to save more energy, right? So you really want to get a handle on these critical paths. So when it comes to dealing with these critical paths or how to even identify them, this is definitely the domain of tools, right? Because our designs are so big, there's so much going on. And also, if you go back for a second, you can imagine there's this combinational explosion of, do we have to consider all possible paths? Going through here, here, here. Okay, what if I go through this way? Okay, what if I go through this way? Okay, what if I go through this way here? And what if I go through this way here? And so there's a combinational explosion there, right? And so this is all kinds of stuff we want to let the tools do. One really, really important tool is something referred to as static timing analysis, or STA for short. So this is the tools taking your synthesized design. So if you're going to do STA, your design has been synthesized to a technology. It may or may not be placed and routed yet. And it has models, right? It knows for the gate how long to take. Okay, the gate takes this long. Or this wire takes this long. Or actually in this technology, if you fan out by this much, it takes this much longer to charge that many endpoints. It has some sort of, back and forth model for all the components. But even though the models for each individual component is simple, in aggregate, is trying to put a model together for your entire system, right? And in static timing analysis, they're going to go through and try to, find these various paths, right? So, for example, let's say you're worried about your critical path. We mentioned a second ago about, all possible paths. That's a, huge combinational explosion. Interestingly, if you're only trying to find the critical path, you can do this in a linear time algorithm, right? So suggested in chat was, this is Dijkstra's. It's not quite Dijkstra, although I'm trying to think about in my head if it might be a little bit similar. I can briefly talk about the algorithm right here, but this is not super critical for this course, but this would be where it exists, right? That there's a way for tools to kind of know, to have models for how long each gate and how each wire takes, and then based on that, determine where your critical path is based on, static analysis, right? Looking at your design without it running, right? And so understand that these models may have certain conservative projections or pessimism to them. And static time analysis may be somewhat conservative, right? And so, would your circuit in practice perhaps be able to run faster? Perhaps it could, right? And of course, also it's not even counter things like manufacturing variability or anything like that. But, it still gives you a good sense of what's going on. And so, for example, let's say you're trying to find a critical path. So how might it work? Well, what you're going to do is you go ahead and in the green, go ahead and mark how long to have these models, right? Models for how long each gate takes. Let's say it takes 4 time units, how long this wire takes. Let's say it takes 5 time units to go across this wire. Then what you're going to do is kind of this back and forth algorithm, right? Where you're going to start at the inputs. What you're going to do is you're going to kind of propagate the circuit through the design, right? It's almost kind of like you're doing a modified breadth first search in a way, right? Or sometimes people in the CAD community might call it a levelized algorithm, right? So let's say, all of our inputs arrive to this, circuit at time 0. And then, okay, well, let's say we go across this wire, right? Okay, so it takes 1 time unit to clear across that wire. So now this input's arriving at this gate at time unit 1. Same for here. And okay, this wire is a little longer. So it reaches this gate at time unit 3. So you can kind of see, for example, given the input arrival times, okay, well, the inputs to this gate were set at 1. This gate takes 4 time units. So this gate's going to have a legitimate output at 5 time units. Now, this is hardware, right? So it's not just, like instantaneous thing. It's always producing an output. It's just from the point of view, what's the correct output? We believe that after 5 time units, this gate should be outputting the correct thing because, perhaps it could be coming out sooner, but, at least after 5 time units because, it came at time 0. We believe this wire can be traversed in 1 or less. This gate can be solved in 4 or less. So thus, kind of this worst case scenario is this output's going to be ready after 5 time units, right? You can kind of apply this algorithms throughout. And what's interesting, let's say, for example, we have a case like over here where the different inputs arrive at different times. Let's say in this case, we're going to be kind of conservative and say, well, guess what? We need to wait for the last arriving input, right? And so, okay, so even though this input arrived at time 3 and you say, oh, it could be ready at time 5, it's not because we're waiting on this other one, which took longer, right? It came out of here at time 5 and it took 5 time units to get through that wire. So it's not going to arrive here until, hypothetically, until time 10 or something, right? Okay, so at time 10, it's the later of these 2 inputs. That's what we're going to kind of do time based on. Okay, well then, after 12 time units, this will be correct, right? And so notice with the static timing analysis, right, we're looking at this kind of just only at these gates kind of as, delay models. We aren't really talking about the specific values, right? You can imagine perhaps a more detailed dynamic analysis might say, oh, wait, if I know this is a 1 coming in here and a 0 coming here, I can do various analyses, or perhaps I notice that our input is later, maybe we'll never reach a certain value and thus I can't change this. These are kind of things we don't need to worry about for now. But with STA, we're kind of being very conservative, right? It's kind of looking at the gates just generally and see what we can do, right? It's kind of like how in coding with software, there's static analysis of code, right? And there's some things that, compilers can detect with static analysis. There's some things you actually need to see data values, i.e. with the dynamic analysis to kind of see what's going on, right? And so with STA here, we are kind of going through it. So you can kind of see the algorithm I described. You can imagine going forward to calculate, these worst case bounds for when its output's going to be stable. And eventually you kind of plug these all in and you get, okay, so our entire circuit takes 23 seconds with this kind of worst case bounding, right? After 23 time units, we know that this output's going to be stable and, assuming our models are correct, it's not going to change again. So at this point, we just know that, the circuit takes 23 time units, right? To actually find a critical path, now we need to crawl backwards, right? So crawling backwards, we're going to go find, each step of the way, we're going to find the last arriving thing. Okay, so this one arrived at time 14, this one arrived at time 15. This is faster on a critical path, so this actually doesn't matter. So we're going to kind of take a longer time, delay one, get here, which one was later arriving, this one was later arriving, we get here, and then these two arrive at the same time, so they're both critical path, right? So actually, if we go back a slide, you can see that, they both are. So the critical path isn't necessarily a single line, right? It can split, it can merge, it can be multiple things. There can be multiple critical paths. If they all take the same amount of time, there's multiple critical paths, right? And so, that's kind of the status with that. Okay, I'll pause for more questions. Cool. Okay. So, how do we go about fixing this critical path, right? So let's say you decide, you're worried about your critical path and, what do you even go about doing it? Well, like I said, we care about critical path because it's set our clock frequency. And like I said, even if we're not targeting a high performance design, if we still can have a short critical path, we can turn down the voltage and still save a lot of energy. So we really want to have a short critical path. Now, what's interesting is if you go out, measure all those various paths in the design, and, actually traverse all those possible paths in that combinational explosion, what you're going to find is that most paths aren't near the critical path in terms of delay, right? The critical path is going to be kind of an outlier in some ways. And even though it's an outlier, it's still going to, limit your design, right? So you really want to kind of narrow your distribution in a way. So if you imagine, distribution, this is kind of a cartoon, as you can see, where, if we're considering all the possible paths in a design and, how long they take and how frequent they are, right? And maybe this is a log scale. So, most paths have a noticeable delay, but not that bad, right? Then there's kind of this long tail of increasing delay paths, right? And so the ones that are longer than your target clock frequency, well, that's going to be ones you need to fix, right? Because if, let's say, you're shooting for a certain clock period, like, we're going to fit our, performance budget, or better yet, performance budget meeting a certain energy budget if we're running at this period, right? If we have this kind of clock. And so these paths are longer. Well, those are reasons why you can't run at that frequency. So you need to run slower and you need to change your design, right? And so naturally, as a designer, our goal is going to be try to change these paths, right? So how can we go about actually making those delays shorter, right? And so typically as a design team, what you're going to do is you're going to go out, and run STA and see where, your longest paths are. And you get a listing of, it goes through this component, this component, this component, this component. And sometimes when you see these paths, you're going to be kind of surprised, but then not that surprised. You're like, wait, where is it going? And you look at your design a little bit and you're like, oh, wait, that makes sense. That's a very long path. That's going to be, perhaps a long wire delay, or it's perhaps going to be touching a lot of things. There's some things that are sometimes very subtle where it's like, oh, wait, this, particular signal I'm using, it's going through so many things. I didn't think of it this way. How it's going to go through so many things, right? And so you want to go and fix these critical paths, right? And so you go find that long delay path, and you're going to find some way to shorten it, right? So you're going to maybe figure out how to change your design, add some registers to pipeline it. You're going to do something, right? And you succeed. And so what's interesting is, after doing a lot of this effort, maybe initially you're going to have a bunch of paths that are longer in your target clock period. After you kind of optimize and change your design, you're going to now, in order to actually run that target period, you better have no paths that take that long. But as a result of, shoving these paths to be just under that deadline, now you're going to kind of have this spike right here, right? So it's kind of like, if you're trying to clean your room in a hurry and, you're doing a good job in the beginning, and then you run out of time and you start, just shoving things in the closet and closing the door and, working really hard to kind of push and shove that closet door shut, right? That's kind of this, right? That's what designers are doing, where they're, we can fix this critical path, we can fix this critical path. In the beginning, they're easy, right? These aren't that bad. These are really egregious. But after a while, it starts getting really, really hard. And so you kind of have this spike here, kind of, mass. And this is one of the situations where, okay, let's see this target period, and you work really hard to fix these long paths so that way your distribution looks more like this. And then, some manager comes in and says, you know what, that's great, but, we're worried about market pressure. We want to go 10% faster. And that's when your designers pull your hair out because, oh, wait, we actually have a lot of paths to fix. There aren't just a couple paths anymore. And we've already tried to fix these paths, right? These paths aren't going to be easy for us to fix. And so when it comes to fixing these critical paths, what I mean by fixing, we'll cover that in the next slide. But I mean, it really depends on what's going on. In some cases, it's not that hard of an intervention. In other cases, it's going to be very time consuming and it's very hard, right? And if you remember from an architecture class, talking about like a CPU when you're pipelining, pipeline is a way to shorten critical path on a CPU, but it has all these challenges, such as hazards, right? Where if you now have multiple instructions in flight, certain things can happen. We're about, the data hazard, one producing data everyone needs. And so there's some of these kind of things that emerge when you're fixing these critical paths. You're going to run into things like hazards, right? And so some of these critical paths are going to be very hard to fix, right? Because by putting a register in there to try and shorten it, you're going to invite other challenges, right? And so you can maybe sometimes meet this clock period, right? But then you're going to do so in a way that perhaps has a lot of bubbles. A lot of times your design can't do anything useful, in which case maybe it's not worth it, right? And so there's a lot of caveats to this, but kind of some key takeaways from learning about this kind of optimization critical paths is that people talk about, where does the effort go in hardware design? Currently, writing design the first time isn't the biggest bottleneck, right? The biggest bottlenecks are, number one, verification and testing. So something we cover very cursorily in this course, but we'll hopefully get to that, a little bit of that next week. And number two is stuff like this, right? So it's kind of physical design optimization, especially for critical paths. This is where a lot of human labor goes into, right? Because the tools can do some things to optimize these paths, but oftentimes they require design changes. And that's where humans have spent a lot of time, wrapping our head around what this path is, and then going about it, right? So, for example, let's say you really want to have that, sub 20 FO4 out of order processor design. You're going to really have an aggressive design team kind of attacking to make sure you meet that target, right? If you're able to kind of go easier and say, you know what, we're able to go at a gigahertz, 800 megahertz, we don't need to push it that hard, life gets a lot easier. And so you might see, for example, you look at academic chips that have been taped out, a lot of them, run at a gigahertz, right? Because to optimize enough to run at 2 or 3 gigahertz is theoretically possible. It's just a lot more engineering effort. And for, academic researchers, that's maybe not worth their time, right? And so, yeah, it's easy to get something running, but to really, trim this long tail and get the certain period, there's going to be some time there. Okay, any questions on this? Cool. Okay, so we talked about delay, how to measure it. So how do you go about fixing these paths, right? And who fixes delay, right? And so this is coming back to one of the themes of this course is I really want to emphasize people kind of working in tandem with the tools, right? The tools are very powerful. Hard designs are only getting bigger and bigger. So in order for you to build a scale to that, you need to let the tools do more and more, right? So I think it's important to kind of appreciate what the tools can do well versus what the humans can do well, right? And so, like I said, CAD tools, EDA tools, there's decades of research and development. Basically all the chips we use are products of these things. Despite me bad-mouthing them in prior lectures, they actually do a lot of things right. And one of the things they do really well is logic optimization, right? There's so much research on that, so much, fine-tuning of those algorithms. It can definitely kind of solve those kinds of problems. They're going to do the Boolean algebra simplification. So when you're writing, your design, think about what's best for you to get, easiest for you to get correct, easiest for you to make readable or modifiable, and let the tools worry about optimizing logic, right? They're going to do that pretty well. And they have a lot of choices that are perhaps invisible to you at the design levels, right? So working at the RTL level, whether it be, Verilog or Chisel, you're kind of thinking, oh, okay, well, what's the logic operation I'm doing here? Understand that when these tools are optimizing, they have a lot of choices, right? Not only can they change your Boolean algebra around to, perhaps shift where the gates are, how many gates are certain things. They also can choose which gates they're using. So in a given technology library, they may actually have different versions of the same gate, right? They may have multiple XOR gates, for example. And some gates may be, very fast, but very big and very high power. Maybe they're going to be smaller and slower or other trade-offs, right? And the tools can do their best to optimize accordingly. A moment ago, I told you, that critical paths that are shorter in the paths that are shorter critical path delay are kind of like invisible in a way because they don't affect our timing, so we kind of don't really worry about them. The tools are going to aggressively try to find those paths and actually, when possible, substitute those gates for gates that are slower but hopefully save energy or smaller. And as long as it meets the timing delay, you're going to be happier, right? Your design is smaller and your design is going to take less power, right? Those are both good things. And so when it comes to these kinds of logic optimizations, right, the tools can do it pretty well, right? And the way I kind of like to summarize this is that if what they need to do is something that's invisible at the RTL level, they're going to do it well, right? So if it's something like, here's my Boolean function, I want you to compute this most efficiently, and it's going to choose, how to break it up and manipulate the logic, how to, which gates to use, it's going to do a good job at that, right? The thing it can't do is it can't change your design intent, right? So, if you say this, Boolean function F needs to produce, A, X, or B, or C, it can't change that, right? It's required to do that. Now, under the hood, it might shuffle logic around a little bit, but it can't change semantics design, right? And so for optimizations, you might think, oh, what if I, did my own K-map by hand, like we teach in CSC 100? No, let the tools do that one. But it can, so basically, if it's not going to change semantic design, the tools can do it. And so just a moment ago, we're talking about things like, reduction trees, right? And we'll come to that later in today's lecture. That's one of those things where depending on the semantics you're going for as a designer, you may be aware of a semantic relaxation that the tools may not be considering because it's not possible based on the way you specified things, right? And this is actually quite similar to even software programming, right? There's cases of software programming where optimizing compilers can do amazing, amazing things. However, inadvertently you might declare things in a way in your code where it makes it impossible, especially in a language like C, for example, where, maybe you have those weak types. It's unable to reason about your pointers to allow for vectorization. Similar kind of thing happens in hardware, right? So, okay, tools can really optimize logic really well, assuming you're, asking it to change the semantics. They can do that very, very well. What can designers do? They can change semantics, right? So what's happening is sometimes when you write design, the way you happen to write the logic out isn't the only way it can be solved. It's just the way you solved it that day. And there may be some corner cases where things are a don't care, but you didn't bother, expressing that to the hardware tools, and so they don't know that. They don't know that that particular semantic is that particular corner case can't happen or that thing doesn't matter, right? And so, you can change design. That's your biggest power, right? You can change design in small ways. You can change design in big ways, right? If you're really trying to reach a really aggressive performance target, you may realize, oh shucks, right? Like we need to make huge, huge changes in order to have a chance at doing this, right? And you really got to rethink your architecture, right? When you have a totally different thing. Like if I'm a processor and I have, an L1 cache, maybe I really need an L2 cache to meet this, particular performance target or something like that, right? And so these are kind of things humans can do best, right? Additionally, sometimes you're going to make changes where all you're really doing is just enabling the tools to optimize more, right? Which is a great way to do it, right? If you can kind of get that, impact multiplier, but then the tools do the work for you, that's great, right? And so, this is kind of a one-slide summary of this, big advanced, skill, but you kind of get the picture here, right? Number one, get your design correct. And then when you actually get to the point of optimizing your design, trust the tools can do things like logic optimization pretty well. And really it's kind of on you to figure out and do the things the tools can't do, right? That's kind of the best place for you to think is, okay, if I'm a human, I'm going to intervene. I'm going to intervene in ways the tools can't do it, and the ways tools can't do it, perhaps something like changing design. Maybe, that the certain, thing doesn't matter, or, maybe you can not use a signal or recompute something. It can do that. Or you can do that, I'm sorry. Okay, I'll pause for any questions. Okay, cool. Let's keep going. So in terms of ways we can fix delay, I think I mentioned some passing a second ago, but now I can talk about this more formally. Pipelining, right? So pipelining is the idea of you have a long combinational path that's going through just gates and wires, and you want to shorten it, right? So going back a second, the critical path is the longest delay path through a circuit. When it comes to your entire design, the critical path is the longest delay path from the output of one register to the input of another register, right? Because that's kind of what's happening, right? We're using registers in the clock to kind of be this, globally synchronized way of, propagating updates in a controlled manner. And so from when a value is produced, or I should say visible for the first time, we want to make sure next time we grab onto the values, we want to make sure this is totally stable, right? Because this is still changing or changes after the clock period, then we're not going to see it, right? And so we have a very long path. If you put a register in the middle, we've shortened the path, right? So we have a shorter path now. Now, sometimes putting a register in is really simple and really easy and definitely shortens the critical path. This is the kind of thing the tools cannot do automatically, right? They can't know that your design can do this, right? And so what's nice about having this, in this case, pipelined? Well, we shorten the critical path so we can increase the clock frequency. Now, if you look at the delay of any operation, right? Let's say like an operand came in here and it goes through your stuff and comes out over here. The delay for that particular piece of data is going to be the same or longer after you pipelined, right? However, the throughput should be increased, right? And so that kind of keeping this point that, wait a minute, I have the same or longer delay, but throughput's increased. How's that possible? Parallelism, right? That when you are pipelining, you have what's called pipeline parallelism, right? You have to have multiple pieces of data in flight, right? If I only have one problem to solve at a time and the data shows up here and I need to solve it, I can't pipeline it because I only have one instance of the problem, right? But if I have, a new problem coming in every cycle, I have, parallelism there, then I can start, associating each, stage or, each level with a different problem instance, right? So you need to have multiple elements in flight. Fortunately, in hardware, usually you have this kind of parallelism. You can do this, right? If you remember from your architecture courses, maybe you have unfortunate memories about pipelining and the challenges involved with that. a processor is almost like the worst case scenario, right? Why is it the worst case scenario? If you think about it, processors implementing an ISA, and ISA is by default a very sequential thing, right? I do this instruction, then I do this instruction, then I do this instruction, I do this instruction. And we know that, advanced processors can do things like looking at the dependencies and dynamically reordering instructions, doing them out of order, but the original semantics of the program was very much sequential, right? And so as a result, there's a lot of dependencies between different cycles. And so that's actually arguably the hardest thing to pipeline, right? And you learn about that, right? You learn, oh my gosh, when you pipeline CPUs, all these challenges about, various hazards and various hazard mitigation schemes and all these other challenges. Fortunately, most of hard design is not that bad. For example, if you're doing something like involving video, well, on different cycles, you're gonna be having different pixels, right? And depending on operation you're doing on those pixels, they may be completely independent, right? Easy to get that parallelism. And you can choose, I have a lot of parallelism, right? And I need to process, a frame of 4K video, right? I have to do, millions of pixels. Okay, if I have millions of pixels, well, I can do some of them over time, different cycles going through the same hardware. I can do some of them in space and just have, parallel units processing different pixels, right? So, like I said, fortunately, in things other than processor design, usually actually is quite a bit of parallelism, and pipelining is not so hair-pulling, right? But it's still not easy. It's still not always trivial, right? Sometimes there's some caveats, some challenges to it. Okay, so when you are pipelining, like I said, number one, you need this kind of parallelism to make this possible, but fortunately, that's quite common in things that aren't CPUs. You also kind of want to balance the delay, right? The whole point is to shorten the critical path. If you put 80% of the delay on one side, then that's not going to help you, right? And so you really want to kind of try and balance it, right? Really kind of cut it in half, right? And let's say, for example, you cut this particular path in half, which is great, and some other path is 80% of long of it. Well, these two paths aren't a critical path anymore. Now you go attack that path, right? And so, and so when it comes to pipelining, like I said, right now, the way we have our languages used and the way we kind of approach things, we need humans to go in and put the registers, right? They need to put registers into design. I wish it wasn't the case, right? If you look at perhaps what maybe the future of hardware design, which is, not just things like chisel, but things one level up, perhaps like HLS, something like that. You can see one of the things HLS does is it tries to free design from thinking about things in terms of time semantics, right? So chisel is a very productive language, but at the end of the day, when you're writing chisel, you are thinking about exact time semantics. Like this particular operation happens on this cycle. This operation happens on this cycle. And I want a wire here and a gate there. And I want a register here, right? You're saying all that, right? Using a higher level synthesis or HLS, you're kind of just giving a functional specification and letting the tools figure out the timing specification. And so I would argue this is definitely the direction we want to be heading, right? I don't know if HLS is quite the right exact solution, but specifying timing and exact detail is a huge source of sunk design effort that I'm not sure that humans do better in tools sometimes, right? And so right now, with classic RTL, like Verilog, VHDL, or Chisel, we're specifying the timing very concretely. There's some really interesting research in future languages, things like TL Verilog, or here at Santa Cruz, our colleague, Professor Jose Renal's PyRope, that have different timing semantics to try and let the tools do more of that kind of in a more interesting way. Okay, that's a bit of an aside, but back to pipelining. I said the goal is, okay, we're going to put registers in design to try to shorten a critical path. The problem is, where do these go, right? And so it depends, right? Sometimes it's really clear, like, this is an operation. It makes sense to put a register right here because kind of conceptually it's kind of a stage. Other times it's not clear where it should go, right? And worse yet, if you're trying to balance delay, like I want to, get in the middle of this long path, how do you know where the middle of that long path is, right? You put the register in one place, and then you run the tools, and then you put the register in another place and run the tools, and it's like, who knows? And also remember that when the tools are optimizing your design, they're going to be, changing, right? They're going to be changing which gates and how they're mapping and optimizing certain portions of the logic, right? So it's almost kind of like you're trying to move around water, where you can push it aside, but in a second it comes flowing back in. It's like that, right? So it's kind of like that, trying to solution around these registers where it's a little bit hard to converge and optimize this sometimes. It's not going to be very labor intensive trying to figure out where to put these registers, not just to even put them in your design, and they're feasible to put it in design, but like I said, in some cases you can't because of hazards. So how can you kind of mitigate those hazards? In other cases, it's just hard to know where to put them. So for knowing where to put them, there's this nice thing called retiming, which is a technology which, is cutting edge 25, 30 years ago and now is like standard, right? So what does retiming do? Well, in the spirit of letting the tools do the work, retiming is a way the tools can choose how to move registers forward and backwards through a giant block of logic, right? And so what they can do is they basically look at the tools know the delays, right? When you're reading your design, you don't know the delays, but the tools do. They've done STA, they know where the delays are, and they can try, for example, moving a register backwards through the logic and kind of shoving the logic on both sides of the register. Now, this is pretty cool. There's some caveats, right? Naturally, it can't always do this, right? There's some topologies where, moving this back through design, maybe perhaps because of the feedback path, isn't really possible, right? And like I said, the tools are constrained to provide you a design that meets the specifications you've given them, the semantics. And so if it's going to cause a breaking change, it can't do it, right? And so sometimes topologies-wise, it can't move the registers around. Additionally, depending on which tools you're using, they have different ways of working. Some people prefer to do what's called forward retiming, where they move the registers from the front through design. Other ones to go backwards. They want the end design and going back through it. Some tools can go both ways. It depends on the tool. So it's one of these things where you need to really know what your particular tool library likes, and better yet, how to specify your registers in a way that makes them amenable to retiming, right? Sometimes they're just kind of very pessimistic checks by the tools. Oh, your flip-flop has a reset signal. I don't do retiming on registers or resets. Might be a condition they may have. So understanding what those constraints and requirements are is important. Okay. What else to say about this? Okay, yes, and this last detail is kind of a small one, but very relevant. If you move your registers around your design, even though at the output of your design you may still have the right result on each cycle, if you're trying to verify your design, this is going to maybe make things harder, right? Because let's say, for example, you say, I'm going to verify that my design has the right value in every register and every cycle internally. Good idea, perhaps, if you don't trust, some of these other optimizations. But now that you move what a register is, what it's holding is actually going to be different, right? And so retiming is really good for optimization reasons, but for verification reasons, you've caused some people some headaches, right? And so because retiming has been around long enough, people are aware of this. And so some of the ways they can deal with this are things like, even though you've moved this register and now it represents a different portion of the design, using, formal verification to kind of prove that, the values here are consistent with the values they should have been if this register was still over here, for example. And so how to kind of, establish these equivalences that even though I move these registers around, which one's supposed to hold which values in which cases. Like I said, you made verification's job harder, but once again, push things onto the tools, out of humans' hands. There you go. Questions? Okay, so for retiming, in the spirit of making tools that work, fortunately in Chisel, we can express this pretty easily. And then the question is that compatible with your tools or not, right? And so a common pattern is to say, I want to parameterize the depth of my module, how many pipeline stages it has. Because, it's a really nice thing you can do with a generator, where historically a second ago I just told you, oh my gosh, it's so much effort to choose where the registers go and how to move them around. It's a lot of effort. I keep running the tools, keep reading Google Path reports. Retiming makes it a lot easier, and retiming plus a generator, that's pretty sweet. Because basically what you can do is you can choose how many registers you want to have in your design. Let's say I want this module to be depth 4, for example, and have 4 deep registers. And then you let the retimer actually move registers through your design, right? And so in particular, what you're going to do is you're going to put registers at the end of your design in this case. Let's say you have a tool that does backwards retiming. So you have the logic you want in your design. You put the pipe at the end. The pipe is, the Chisel library way of saying, a shift register. In particular, a pipe is, completely, fire and forget. There's no enable signal, no stall signal, no reset signal. That thing is just, it comes in one cycle, goes out the next cycle, boom. This keeps going through, right? And so you have this, stack of, unadorned, unmodified registers at the end. Let the tools pull them back into design with backwards retiming. Like I said, some tools may want us at the front, but you kind of get the picture here, right? And so yeah, you're gonna have your logic, stack registers at the end, and let the tools pull them through design for retiming at the timing. So this is pretty cool, where, in the past, we've had people spending a lot of time learning about optimizing a certain unit. Now, if a generator, you can have, let's say some big complicated thing, and you can set this knob, right? And someone using it can say, you know what, I'm going to try at depth 4, try at depth 6, depth 3, try them all out, depth 5. And just kick them off a bunch of different tool runs. Really easy to change the human to change the depth in the code, right? And then the tools are going to optimize and you see what comes out, right? You say, oh, wait, if I use depth 3 in my design, I don't make timing, but if I use depth 4, I do. I'm not going to bother at depth 5 or 6. That's extra hardware, right? And so this is one of those kind of places where you get a real big time benefit from a productivity boost from using something like Chisel, where you can very easily specify something like this depth for your pipeline and then let you use things like the retiming to try and balance it, right? And so retiming is a really robust feature on any reasonable ASIC CAD tool. On FPGA CAD tools, support varies, and it can be kind of cranky. So, for example, Xilinx Vivado, which my research groups had quite a bit of familiarity with, it retimes only under certain circumstances. You have to be really careful to understand that you aren't inadvertently giving us a problem that thinks it can't retime, even though it can. It's a little bit more brittle, but cool. Any questions? Great. Okay. So, earlier I said, what can tools do well versus humans do well? One of the things humans can do well is we can change the design, right? There's places where, the tools would want to optimize it, but they can't do it because that would change the rules of design. And so as a human, we can do that sometimes, right? And so this is one of these things where humans are often oblivious to what they're asking the tools, and that there's certain constraints they're imposing they don't really care about. And so trying to be aware of those things are and looking for inefficiencies is kind of an important thing, right? And so one place where delay can really grow up very big, right? A lot of times delay is kind of intrinsic, you do certain operations and it's kind of hard to fix, but that's only when you've been optimizing for a while, right? When you're first looking at your first timing report, you're going to see some long delay paths that are, trivial and you should go fix, right? And so some of those would be things like things where the logic depth seems to grow linearly, right? And so in the, example we've seen so far in this course, you see me do a lot of things with recursion or for loops where we kind of things like our own, pipeline shift register kind of thing. And, we did those linearly because that's what we're just trying to do, and we didn't really think about it. We remember we use fold left, for example, to try and do stuff, right? That could be linear, depending how we use it, right? And so if its linear number is small, it's only 3 of them, fine, right? And your critical path is elsewhere, fine. But sometimes, if that's depth 1,000, that might be your critical path. It might be a big critical path. Might need to figure out how to kind of handle that, right? And so naturally, if you have these kinds of delays, we just spoke about pipelining as one option. If you have something that grows linearly, you may be able to make it grow logarithmically by using some sort of tree structure, which is we're going to show in the next slide. But either way, like I said, my advice has always been close the loop, get something running, get it correct, then we're worried about optimizing. And when you're optimizing, not only should you be starting from a correct design before you're optimizing, you should also have a way of measuring it, and you should be convinced that this particular thing you're fixing, if you do change it, will yield benefit, right? And so, for example, if you're looking at a path and you're, this is a really high delay path, I should go fix this. If it's not currently your critical path, don't touch it yet, right? Because realize that it doesn't matter. The critical path is what matters. Now, perhaps after you optimize, 5 critical paths, and that then becomes your critical path, then is when the time you deal with that thing, right? That's because something makes you feel nervous. The tools may be handling it really well, right? The tools may actually be able to optimize it. It may just not be the critical path. You may not know the constants, right? Maybe this thing which you think is really expensive is actually really easy to do for the logic. It doesn't take a lot of time. So yeah, if you're going to do any kind of optimization, make sure you measure it and design is correct to start with before you even start doing this. But let's say you've done those things. And then what can you do? Well, we're going to see an example of that. So in our example is this reduction problem, right? Where you have some collection of numbers. In this case, let's say you have n numbers. It almost sounds like a technical interview question. They say, hey, I have n ints, right? But that's kind of what we have here. And you're asked to add them up, right? So we showed examples using things like fold left, where we go in and, add them all together in this big linear sequence, right? Now, if you do it in a split linear sequence, right, this is depth n, which, if n is big, this is a lot of delay, right? Now, moving to a tree-based structure, this becomes logarithmic in depth. And what's also interesting about this is that this doesn't require more hardware, right? This can be done in a way where you can kind of pull them together, right? Yeah, and someone was even bringing this up in no bit of context in this case. That makes me chuckle. But a student pointed out that they actually received an interview question literally about 2-to-1 muxes and linear versus tree. So yes, this is definitely a concern, right? And so the tree looks great. And the interesting thing with the tree is that it actually doesn't require more hardware, right? If you think about it, part of what linear is getting wrong is that you are, for each additional adder, you're only getting one more input, right? Versus with the tree approach, right? You're putting 2 inputs per adder. Yes, you're kind of funneling them together, but it actually takes about the same number of adders, right? And so the tree seems great. So why wouldn't the tools just automatically do the tree? In many cases, they can, right? For example, let's say you're doing something involving logic operators like and or, it definitely will do that. So why wouldn't it do that for add? Well, goes back to the thing I said a few minutes ago about changing the design semantics, right? So for addition, if you add 2, let's say, n-bit numbers, in the worst case, the result could be n plus 1 bits, right? If I add 2 8-bit numbers, it actually could overflow and thus become a 9-bit number as a result of that addition. If the output of my addition is saved to be the same size as the inputs, in this case, let's say 8-bit inputs, 8-bit output, it's possible that there's this overflow behavior, right, where I have 2 numbers added and the result appears to be smaller than the inputs because it's wrapped around. That's semantics, right? And so if I give my tools a design in which I have these numbers doing this addition, which because of the size of the inputs and the outputs, overflow is possible. Let's say the input and output sizes are the same. If I accumulate these things in a linear order versus in a logarithmic order, that actually changes the numeric result at the end, potentially, depending on how the overflow works out, right? And so yes, if there's a case where, different inputs gets different output, that's something the tools can't do, right? Like they can't change the design in a way that's going to cause you to see different outputs, right? That's something they don't want to do. Now, you as a designer might know that, these numbers, despite being 8-bit signals, are never going to be that big. Or if it does overflow, you're okay with that. That's something that the tools don't, right? This is kind of situations where you maybe do need to intervene. Another alternative might be, well, what if I don't truncate the addition, right? So, instead of having 8-bit input, 8-bit output, it could be 8-bit input, 9-bit output. And so then the question is, well, how big should it be? Well, if I did things linearly, and I could end up with a additional n bits on the output width, which maybe would be unreasonable if this n is big, versus if I did this way, it would be another log n bits, right? Which actually would not overflow, which would be great. But once you can kind of see how this plays out. So this is kind of a detailed example, but I want to kind of show us an example of where, as a designer, there's some intent here that you didn't intend that is constraining the tools, right? That, like I said, if you have truncating addition, which usually is the right thing to do for many situations, that's imposing certain semantics. When you choose to do that reduction in a certain way, the tools can't do that transformation into a tree for you automatically. For logic ops, like and or, it often can because of associativity and commutativity and that kind of stuff, right? But like I said, if you're truncating addition, you lose that associativity, and thus you kind of have that problem, right? Okay, so let's say we want to have this tree. Well, how would this look? Well, why don't we actually do this really simply and chisel ourselves, right? So in this case, what we're going to do is something called pop count. Pop count is another way of saying counting the number of bits in a number that are 1, right? So, if let's say the number 2, well, we know that 2 in binary is 0, 1, 0, so it's a pop count of 1, as opposed to 3 is, 0, 1, 1, so that'll be a pop count of 2. Yes, as the student's pointing out, I'm, answering all their interview questions. Perhaps they're reading my slides, I don't know. Okay, so pop count is a common operation. Maybe if you've read this book called The Hacker's Delight, you've learned how to do this really efficiently in C. But, pop count, the simple operation is kind of easy to describe. Like I said, the goal is to count how many bits in a number are 1, right? And so, well, how might we do this? Well, if we did this linearly, what we would do is we would say, hey, we take in this case, a sequence of bools, right? So this isn't even a vec. This is just a collection of wires. We want to know how many of those wires is 1. Well, we'll solve it recursively, right? So what we'll do is we'll say, hey, we'll take the, for every number, if we're empty, we'll reach the base case. We can just go ahead and add a 0. But if we're not empty, let's go ahead and take the number off and then add it to this thing. So you can see this is going to produce a linear sequence, right? And yeah, if we call in our, count ones module, we can see it's basically just going to, instantiate this different pop count thing. Okay, so let's go ahead and run this, put the compy to work, zoom out so we can see the code. And, it actually is doing that, right? And so you can see, in this case, where are these ones or zeros padding coming in? This is the chisel using the non-truncating addition. If I take this off, it's just going to do the additions. And you see the output is going to be a result of, in 0 plus T5, T5 is T1 plus T3, T3 is in 2 plus T0, and T0 is in 3, right? And so, let's say we're, being consistent, we're going to go ahead and use that non-truncating addition. There we go. Okay, so that's the linear approach, right? And let's say if this is small, like I said, if I'm only doing 2, right? This actually works out pretty well. But then, as we can imagine, if I was to do this right, soften the prior slide, make this really deep, we're going to not only have a lot of code, but it's this big linear depth, right? So this could become a critical path. Okay, so let's go ahead and think about how to do that tree approach, right? We just kind of showed it. Conceptually, we want to kind of add them up in a tree. So then how might this look? Well, all right. If we're working this in a tree fashion, rather than doing only 1 per recursive call, we're going to do half per recursive call. So, if there's only 0, 1 elements left, then, we kind of have these base cases, right? If we have 0 elements left, we need to just, call that a 0. If we have 1 element left, we have 1 thing to process. Otherwise, what we're going to do is we're going to take the first half and the second half, right? So take and drop are, operations on the chisel collection. And so take takes the first n elements you tell it to, and drop takes the next n elements, right? And so, in other words, it drops the number you give it and it takes the ones afterwards. So, here I chose to use the Scala syntax of using the space and no punctuation. This could just as well have been like that. But yeah, basically say, hey, let's do this tree pop count on both halves. As you can see here, I'm citing my source for stealing this code from the chisel library. Okay, so let's go ahead and try out this tree version.